If you watch a modern CNC lathe at work, it's practically a ballet.
Oh, totally. It really is.
You've got this massive chunk of raw steel spinning at just incredible speeds. And these cutting tools are just gliding across it.
Yeah, the machine is basically imposing its absolute will on the metal.
Right. Sculpting complex curves, cutting flawless threads, making these perfect sweeping tapers. It looks entirely effortless.
It does. But there's a fluidity to it that really hides the violence of what's actually happening at a microscopic level.
Yeah, it looks like magic to us. But then, at the very end of this beautiful, intricate process, the machine just has to slice the finished part off the remaining bar of metal.
Like the parting phase.
Yeah, it just has to cut it in half so the finished piece can drop into the parts bin.
Which, sounds like the absolute easiest, most basic part of the whole operation. You're just cutting a line.
Exactly. But instead, that final slice is an absolute physics nightmare. So welcome to today's deep dive, you guys. We are looking at a highly detailed technical document today called Mastering the Challenges of Parting and Grooving Operations.
That's a great paper.
It really is. And our mission today is to uncover the hidden, fascinating engineering happening right behind the scenes of everyday objects you use.
Because a straight cut is never just a straight cut.
Never. We are taking the seemingly mundane act of parting a piece of metal on a lathe, and we are going to discover why it actually requires synthetic diamonds, star-shaped geometry, and microscopic engineering just to make it work.
It's a perfect example of how the things we take for granted are often the most complex.
So true. Okay, let's unpack this. Why do engineers treat cutting incredibly complex shapes like taper turning or profiling as standard everyday procedures, but they view simply slicing a piece of metal in half as this overwhelming challenge?
Well, it really comes down to a fundamental deception about what the tool is actually experiencing. Well, in the manufacturing world, those complex operations you mentioned, like longitudinal turning or facing, those are the main events. They get all the glory and all the engineering focus.
Right.
Conversely, parting and its close cousin, grooving, are often mistakenly dismissed as simple auxiliary operations.
They're just an afterthought at the end of the day.
Precisely. You'll literally see them categorized as just related to turning processes in some textbooks. But parting starts with a fundamental inherent paradox that you just don't face in those other operations.
A paradox?
Yeah. Think about the economics of manufacturing for a second. When you cut a part off a bar of metal, whatever metal is removed by the width of your cutting tool is instantly turned into scrap.
Oh, it's essentially sawdust.
Exactly. It's metal sawdust.
Oh, I see. So if you are making, say, 10,000 steel bolts and your cutting tool is an inch thick, you are throwing away an inch of solid steel between every single bolt.
Which is incredibly expensive.
Yep.
So to save money and reduce material loss, you want that cutting tool to be as incredibly thin as physically possible.
Okay, yeah, that makes perfect sense.
But here's the paradox. As the workpiece you are trying to cut gets thicker, the tool has to reach further into the center to actually sever the part.
Right, it has to go deeper.
Exactly. So your tool must be longer. It requires what we call an extended overhang.
Okay, I want you to picture this if you're listening right now. Imagine trying to slice through a massive spinning block of very dense, hard cheese.
Okay, I like where this is going.
But because you want to save as much cheese as possible, the only tool you are allowed to use is a flimsy, incredibly elongated razor blade.
That is a highly accurate, if slightly terrifying, mental image.
Right. It sounds impossible.
It is. And here is why that matters so much from an engineering perspective. A slender, protruding tool has inherently low rigidity.
And rigidity is a big deal.
In machining, rigidity is everything. If the tool flexes even a fraction of a millimeter, it destroys your machining stability.
Because it just starts bouncing off the metal instead of cutting it smoothly.
Yes. It creates vibration, or what machinists call chatter. And chatter is catastrophic.
I can imagine.
Yeah, it can shatter the delicate cutting tool entirely, or at the very least, it ruins the surface finish of the part you just spent 10 minutes perfectly sculpting.
Just because it's dangling out there in space, taking all this force. But it's not just the shape of the tool that's the problem, right? The actual environment the tool is entering seems like a completely different world than the rest of the machining process.
So the environment inside that cut is uniquely hostile. When a tool is turning the outside of a cylinder, just peeling a layer off the top, the metal chips can just fly away into the open air.
Right, they just shoot off into the machine enclosure.
Exactly. But in parting and single-pass deep grooving, the tool plunges directly into the solid workpiece.
So it's basically digging a trench.
A very deep, very narrow trench. And now instead of just the front tip cutting, you have solid material rubbing against both sides of the tool simultaneously.
Oh, man. So it's getting squeezed.
Yeah, which intensifies friction to an extreme degree. And where you have extreme friction, you generate a massive thermal load on the cutting edge.
And heat is a big deal here. Doesn't heat eventually just melt the tool?
Well, it softens the cutting edge, which causes rapid wear. And eventually, yes, you get plastic deformation of the tool itself. Heat is the absolute worst enemy in machining.
But wait, I've seen these machines run in person. They have those little hoses spraying white liquid everywhere. Can't you just blast that trench with a high-pressure jet of liquid coolant?
You can try, but the nature of a parting operation complicates effective coolant delivery immensely. Think about what you are targeting.
Okay.
You are trying to spray a liquid into a deep, incredibly narrow trench. But that trench is spinning rapidly.
Right, it's spinning at like 1,000 RPM.
Which creates a centrifugal barrier of air. Furthermore, the trench is actively, violently ejecting hot metal chips outward at the same time.
Oh, wow. So the coolant is fighting this wall of air pressure and a literal geyser of metal shavings just to get in there.
Exactly. The coolant often just gets deflected away at the surface. It completely reduces its cooling and lubricity effects right down where the actual cutting is happening.
Which actually brings up a question about those chips. If you're digging a deep trench in solid steel, those chips have to get out somehow. What happens if they don't?
If the chip doesn't evacuate perfectly, it jams inside the groove.
That sounds bad.
It is. Because the machine is constantly pushing the tool forward. A jammed chip means the pressure spikes instantly, and your flimsy extended tool just snaps in half.
Jeez. So how do you stop a continuous ribbon of steel from jamming in a tiny trench?
This is where microscopic engineering comes in. The flat top of the cutting tool, which we call the rake face, can't just be flat. Engineers have to design a highly specific topology onto that tiny surface.
Like a landscape?
Exactly like a landscape. It has very deliberate ridges and bumps designed to forcibly bend the continuous metal chip into a tight curl until it breaks.
Oh, it forces it to fold over on itself.
Yeah, it snaps the continuous ribbon into small, manageable pieces. They're often shaped like little 6s or 9s.
It's amazing.
It is. And because they're broken up, they can flow smoothly out of the groove without scratching the machine surfaces or jamming the tool.
Okay, so you have a flimsy, vibrating blade trapped in a deep, boiling hot trench, fighting centrifugal air barriers just to get a drop of coolant, all while meticulously folding and snapping metal chips.
It's a lot going on.
It is. And yet, looking at the source material, none of that is even the craziest physics problem happening here. We have to talk about the geometry of a spinning circle.
Ah, yes. This is one of those counterintuitive physics realities that really catches people off guard. It's the RPM problem.
Think of a vintage record player you might have in your living room. The outside edge of a vinyl record is traveling much faster over the needle than the area right near the center label.
Even though the whole record is spinning at the exact same RPM, say, 33 revolutions per minute.
Right. That is the perfect way to visualize it.
And the exact same thing happens on a lathe. The spindle might be turning at a constant, say, 1,000 RPM.
Okay.
But as the cutting tool moves deeper into the groove, moving towards the central axis of the workpiece, the diameter of the circle it is actively cutting is constantly decreasing.
Meaning the actual cutting speed, like the physical speed the metal is moving past the cutting edge in meters per minute, is dropping rapidly.
Correct. And a cutting tool is designed to work at a specific optimal speed to shear the metal cleanly.
So if it goes too slow?
If the speed drops too low, the metal starts to tear instead of cut. And here's the ultimate mathematical paradox.
I'm ready.
As your tool reaches the exact dead center of the spinning workpiece, the diameter becomes 0.
So the cutting speed becomes 0. The metal isn't moving past the tool at all anymore.
Right. And unless the CNC machine can continuously speed up the spinning chuck to compensate, the cut just fails.
But wait, so even with million-dollar ultra-modern CNC machines that can automatically adjust their spindle velocity, you still have this problem. Can't they just spin faster as the tool gets deeper?
What's fascinating here is that while modern CNC machines do try to compensate with adjustable spindle velocity, you simply cannot defeat the physics.
Because it would have to spin infinitely fast.
Exactly. There is a mechanical limit to how fast a massive steel chuck can spin before it literally flies apart. You cannot reach infinite RPM.
Right, obviously.
So the cutting speed will always inevitably drop to near 0 at the center, which leads to a phenomenon known as the pip.
The pip. I love that term. What exactly is a pip?
When the tool reaches that central area of the workpiece, the remaining material connecting the finished part to the main bar becomes an incredibly thin, fragile column.
Like a tiny little thread of metal.
Yeah. And because the cutting speed has dropped so low, and because the tool is still pushing inward, eventually that tiny column of metal becomes too weak to resist the radial force of the cutting tool.
It just gives up.
It yields. It can't be cut cleanly anymore. It just snaps. And when it snaps, it leaves a small, ragged nub of material on the center of the finished part.
And that nub is the pip.
That is the pip. Every single time you part a spinning object, you get a pip. It is an unavoidable reality of physics.
So if you can't beat physics, what do you do?
Well, the engineering challenge isn't eliminating the pip entirely. That's impossible.
Right.
The challenge is designing the tool's geometry, its sharpness, and managing the machine's feed rates so that the inevitable pip is as incredibly small as possible.
Minimizing the need to, like, sand or grind it off later by hand.
Exactly.
Okay, so we've established these are nightmare conditions. You're fighting friction, heat, chip evacuation, and literally the mathematical limits of a spinning circle.
It's a miracle it works at all.
Seriously, and when these flimsy, extended tools inevitably dull or snap, how does the industry actually fight back? Especially considering the raw materials used to make these cutting tools are getting incredibly expensive.
Right, this raises a really important question about the economics of modern manufacturing. The primary material used for high-performance cutting tools is tungsten carbide. It is incredibly hard and can withstand massive temperatures. But the global price of tungsten has risen to very significant levels over the years.
I imagine.
You can't just throw a massive, solid chunk of expensive tungsten at a problem anymore. Its rational utilization is critical to a factory's survival.
You have to be super smart about how much tungsten you're throwing away when a tool gets dull.
Exactly. And this is where a company named ISCAR enters our source material. They became pioneers in this specific field way back in the 1970s with a product family called Self-Grip.
Right, I saw that. So instead of the whole long blade being made of expensive material, just the tiny cutting tip was a replaceable insert, right?
Yes. The main body of the tool is just standard steel, but the very tip is a small piece of tungsten carbide held in place by friction and cutting force.
Which was a massive leap forward, I'm sure.
It was. But let's jump to their modern breakthroughs to see how they've handled the rising costs and the extreme physical demands we just discussed. They developed product lines called PentaCut and the newer Quick Penta.
Yes, the document had pictures of this, and it completely subverts what you think a cutting tool should look like.
It really does. Instead of a long, straight blade with a tip on the end, the Quick Penta uses a star-shaped carbide insert. It literally looks like a 5-pointed star.
It's like having a 5-sided, absolutely indestructible razor blade.
It is brilliant from both an economic and an operational standpoint. Because it's a star, that single piece of tungsten carbide provides 5 indexable cutting edges.
Meaning you use one point of the star to plunge into the trench and cut thousands of parts.
Right.
And when that specific point finally gets dull from all the heat and friction, you don't throw the whole insert away.
Nope. You just loosen a screw on the side, quickly rotate the star to the next sharp point, tighten it down, and go right back to work, which maximizes the use of that expensive tungsten carbide. Every gram of the material is utilized. But the Quick Penta specifically introduced a new fixing mechanism that increased the clamping stiffness of the star itself.
Oh, this goes back to our rigidity problem. The flimsy cheese-cutting razor blade.
Exactly. The new clamping design provides such enhanced rigidity that you can index the insert, rotate it to a new edge, without even fully removing the clamping screw.
Wow, so it's incredibly fast.
Fast and highly precise. And because it is so rigid in the holder, the tool isn't just limited to straight parting and grooving anymore.
Wait, it can do the fancy stuff too?
Yes.
Okay.
It has enough stiffness to handle light turning operations, moving sideways along the bar as well.
So it's super versatile. You don't have to change tools in the machine as often, which has to save a factory massive amounts of time.
Totally. And crucially, they designed the tool body holding the star to feature internal coolant delivery, including high-pressure coolant or HPC.
Oh, wait. Remember the centrifugal air barrier we talked about earlier?
Right, the coolant bouncing off the trench?
Yeah.
Well, this system shoots the high-pressure coolant directly from tiny channels inside the tool body, right underneath the metal chip, directly at the cutting edge.
So it completely bypasses the air barrier.
Yes, blasting the heat and blowing the chips right out of the groove. Plus, it's backward compatible with older PentaCut holders.
Which is a huge financial benefit for machine shops that don't want to replace all their existing hardware.
Exactly.
So the star shape brilliantly solves these big industrial scale economic and rigidity problems. You can cut big, heavy steel bars efficiently.
Right.
But here's where it gets really interesting. What happens when you scale all of this down?
Micro machining.
Yeah. What happens when you aren't cutting a massive steel drive shaft for a truck, but you are cutting microscopic components for things like pacemakers or smartphones or tiny gears in Swiss watches?
Oh, then you enter the world of Swiss-type machines and compact lathes. These machines are working with very small diameter bars of metal.
Okay.
And when your raw material is tiny and potentially made of a highly expensive medical-grade titanium alloy, maximum material savings become absolutely paramount.
Yeah, you cannot afford a thick cut because the scrap you are throwing away might be worth way more than the part you're actually keeping.
No, not at all. You need minimal cutting widths. So ISCAR developed a line for this extreme micromachining called the Mini Quick 2-Cut tools.
The ones that are incredibly thin.
Yes, they are designed for extreme material savings, performing cuts as narrow as 0.33 millimeters.
Hold on, 0.33 millimeters. Let me just do the math on that for a second. That is like, what, the thickness of maybe 3 sheets of standard printer paper stacked together?
Basically.
That is 0.013 of an inch, and the source says they only go up to just 2 millimeters thick.
And remember our paradox. To cut deep enough to sever a part, a thin tool must have a long overhang. It has to stick out.
So how do you make a tool that is as thin as 3 sheets of paper, rigid enough to plunge into solid metal without snapping instantly?
That's the million-dollar question.
Right. If rigidity is everything, how does a 0.33 millimeter blade survive that trench without vibrating into dust?
The mechanical genius here is a concept called tangential insert mounting.
Okay, let's unpack this. Tangential mounting.
Normally, an insert sits flat on the tool holder, and the cutting force pushes down on the top of it, pressing it into the pocket.
Okay.
But with tangential mounting, the insert is rotated 90 degrees and located on the side of the tool.
Okay. If you are listening, I want you to visualize something with me. If you grab a standard wooden ruler off your desk right now,
I love this analogy.
if you lay that ruler flat between 2 books, making a little bridge, and push down on the flat middle with your finger, it bends easily, right?
Right. It has no rigidity in that direction.
Exactly. But if you turn that same ruler on its edge, so the narrow part is pointing up and down, and you push down on that narrow edge, it won't bend at all.
It can hold a massive amount of weight.
Yes.
That is a perfect analogy. The tangential tool design uses that edge-on strength. The cutting force is directed down the longest, strongest axis of the carbide insert.
That's so smart.
It really is. Furthermore, the rear section of this tiny insert is V-shaped and features a protruded boss that seats securely into a specially formed pocket on the tool holder.
So it's totally mechanically locked in.
Exactly. This design forces the main cutting forces to be absorbed directly by the robust datum surfaces of the heavy tool body itself.
Whoa, back up. Robust datum surfaces. You're losing me there. Is that just a fancy way of saying the structural foundation of the tool holder?
Oh, I apologize, yes. In engineering, a datum surface is basically the primary structural reference point.
Got it.
By locking the insert into these solid, heavy steel walls of the tool body, the heavy steel takes all the punishment. It heavily reduces the load that is placed on the tiny clamping screw holding the insert in place.
Oh, I see. It completely bypasses the weak point. Because if the screw had to take all that force, it would just shear right off.
It would. The result is excellent rigidity. It absorbs all that tangential force, which ensures smooth, safe cutting with high-dimensional repeatability.
Even at those microscopic 3 sheets of paper widths.
Exactly. And incredibly, they still managed to pinpoint high-pressure coolant right at the cutting zone through the tiny tool body for chip evacuation.
It's just astonishing what they can do. So, okay, we've solved the geometry, we've got star shapes for the big, heavy stuff, and we have tangential edge-on mounting for the microscopic stuff.
Right.
But what if the problem isn't just the physical shape of the tool, but the actual metal you're trying to cut?
This is where we transition from the structural shape of the tool to the molecular makeup of the cutting edge itself.
Let's talk about aluminum for a second. Aluminum is lightweight. It's everywhere in aerospace and automotive manufacturing. But from a machining standpoint, it is incredibly sticky and abrasive.
Very much so. It falls into what the industry calls the ISO N group of materials.
ISO, is that just an industry category for aluminum and stuff like that?
Yes, it's the standard classification for aluminum, copper, brass, and other non-ferrous metals.
Okay.
And the problem with ISO-N materials is that when you cut them with standard tungsten carbide, the extreme friction causes the aluminum to actually heat up and weld itself directly to the cutting edge of the tool.
Wait, it permanently sticks to the blade?
It forms what's called a built-up edge. It literally changes the microscopic geometry of your perfectly sharp tool into a blunt, sticky mess.
That sounds like it would completely gum up the works.
Oh, it ruins the cut entirely.
So how did ISCAR upgrade their classic DuGrip line to handle this sticky situation?
By moving past tungsten carbide entirely for these materials and upgrading to PCD inserts.
PCD, which stands for?
Polycrystalline diamond.
Diamond. Literally the hardest material we know of on Earth.
Yes. PCD is vastly harder and far more wear-resistant than tungsten carbide. Because it's so hard, the abrasive nature of aluminum barely scratches it.
Which results in a considerably longer tool life.
Right, but hardness isn't its only or even its most important advantage here.
Right, because we are still fighting heat in that trench.
And this is the key. PCD has vastly superior thermal conductivity compared to tungsten carbide.
Okay, why does thermal conductivity matter so much here? Does that mean it just survives the heat better?
No, it actually means it actively pulls the heat away from the cutting edge much faster. Yeah, it transfers the heat out of the friction zone and into the body of the tool where the coolant can hit it.
That is amazing.
Because it pulls the heat away so efficiently, the aluminum at the cutting edge never reaches the temperature required to melt and weld itself to the tool in the first place.
That is brilliant. It defeats the built-up edge problem thermally, not just mechanically.
Exactly. And when you combine that thermal management with its extreme hardness, it allows manufacturers to run the spinning lathes at much, much higher cutting speeds.
Significantly boosting productivity.
You got it.
But speed brings a new problem with aluminum. I've actually seen this in machine shops. When you cut aluminum fast, it doesn't want to break into nice little manageable chips like steel does.
I know, it certainly doesn't.
It naturally wants to form long, continuous, incredibly sharp, stringy chips.
They literally look like massive, razor-sharp steel wool ribbons just flying everywhere.
And they are so dangerous. They wrap around the spinning chuck, they whip around and break sensors, they clog up the machine, they ruin the part. You absolutely have to break those chips.
You do.
But earlier, we talked about sculpting a topological landscape onto the rake face to break chips. We just said this tool is made of diamond. How on earth do you shape a complex chip breaker onto a diamond?
If we connect this to the bigger picture, this is where material science and mechanical engineering are merging in truly astonishing ways.
Okay, I'm listening.
ISCAR's ultimate innovation here wasn't just using a flat piece of PCD. It was successfully incorporating a 3D chip breaker geometry formed directly onto the PCD rake face.
They essentially sculpted a microscopic speed bump directly out of synthetic diamond.
They did.
How?
Utilizing highly advanced manufacturing techniques like laser ablation, they could actually vaporize tiny amounts of the diamond to carve out that landscape.
Vaporizing diamond, that is insane.
And that integrated chip breaker greatly enhances the chip formation. It physically forces that long, stringy, high-speed aluminum to curl aggressively back on itself and snap into tiny, safe fragments.
It turns a chaotic, stringy, dangerous mess into a stable, efficient, and safe operation, all by laser carving diamond.
Exactly. Additionally, that specific geometry helps reduce the cutting forces and the friction even further. Through focused innovation in both macroscopic tool design and advanced molecular material science, operations that were once dismissed as simple have been completely redefined.
Well, so what does this all mean? Let's take a step back and look at the journey we just went on today.
It's been quite a ride.
It really has. What started as a seemingly basic slice, just cutting a piece of metal in half, has taken us through the intense physics of thermodynamics, friction, and centrifugal barriers.
It covered a lot of ground.
We saw how the rising economics of global tungsten forced the clever invention of five-sided star-shaped geometries. We looked at how tangential edge-on force distribution allows a blade the thickness of 3 sheets of paper to slice solid metal without shattering.
Right.
And we ended with the incredibly precise reality of laser sculpting chip breakers into synthetic diamonds to tame the heat of aluminum.
It is a phenomenal, almost unbelievable amount of engineering dedicated to a single, fleeting, critical moment of manufacturing.
And I really want you to think about this today as you go about your life. Every manufactured metal object you interact with, From the heavy engine block in your car, to the hinges on your laptop, down to the tiny microscopic screws holding your smartphone together.
Every single one of them.
Yeah, all of them relied on these exact invisible battles between heat, friction, and tool geometry to even exist in your hands today.
It really does make you look at the physical world differently.
It totally does.
And honestly, it leaves me with one final fascinating question based on where the source material points.
Oh, lay it on us.
Well, if we are currently at the point of synthesizing and laser carving diamond geometries to handle cuts on a millimeter scale, just to deal with the extreme limits of physical friction and heat, what happens when manufacturing scales down even further?
Oh, wow.
Will the future of parting operations eventually have to abandon physical cutting tools entirely? Might we see a shift in the coming decades toward manipulating materials at the atomic level, or using highly focused energy like advanced lasers or plasma to separate materials without ever having a physical tool actually touch the metal?
A future where we don't have to worry about a microscopic razor blade in a block of cheese at all. I love that. Thank you so much for joining us on this deep dive into the hidden world of manufacturing. Go look at the metal around you with a new appreciation, and we will catch you on the next one.